because we now move to Van Komurka. Van has, after today, to his credit, that he has made the most presentations in this series. I think, Van, if I remember correctly, this is your third one. The first two were very interesting, and we're looking forward to hearing your third one today, dealing with the field testing comparison of four-driven pile types. The floor is yours.
Thank you, Gerald, and thank you all for attending this webinar online. It's a privilege and an honor to be able to present it. I hope that you find it interesting and get something out of it. We're going to, in outline of what's going to be presented, we're going to give an overview of the test program, and then we're going to go over how long-term allowable load profiles were developed. We're going to define a concept that allows apples-to-apples comparison of the economics of viable foundation types. So we're going to define pile support cost, and then we're going to look at the pile support costs that came out of this particular case history. And then if there's time, we'll talk about shaft setup, both magnitude and time rates of the various piles included in this test program. This is more of an intellectual interest than a key to the value engineering. And so we'll take that last bullet point only if there's time. So let's jump into the test program overview. The Minnesota DOT contracted the firm HDR to perform what they called a CRAVE study, cost, risk assessment, and value engineering, for this bridge. And it involved all aspects of the bridge, but regarding the bridge foundations, the CRAVE study recommended that a pre-construction pile test program be performed, that various pile types be included in that test program, various pile types, lengths, and at various locations across the bridge footprint. And that within that test program, capacity, both initial and setup, be determined. And the Minnesota DOT was also interested, as long as we were doing the test program, to develop shaft setup profiles, that is, shaft setup as a function of depth or elevation, and time rate of setup. So we were contracted to simply perform the test program. We weren't involved in the final design or installation of the bridge, but to perform this particular recommended test program. So in terms of project location, this probably doesn't mean a lot to a lot of folks. This is St. Paul, Minnesota. Here's the Mississippi River. We had multiple test sites. These sites north of the river included limited number of piles, maybe just 2 or 3 piles at each one of these locations, and no static load testing was performed up here. We're going to focus on site A down here south of the river. So that's where our test program took place, just south of the Mississippi River. This is a schematic of the test piles that were driven. Let's note a couple things before we talk about the individual pile types. First, here's a boring log, very proximate to the test site, so the soil conditions were well defined. These 4 piles were driven as reaction piles first, and then 2 pairs of potential test piles were driven, these 2 and these 2, and then depending on how these drove and what we wanted to learn from which ones may make better static load test piles, these 2 were selected for static load testing, and then another group of reaction piles were driven out here. So that gave us the option of deciding which pair among these 2 pair would get tested by which side we drove this second set of reaction piles on. And then so that's kind of the philosophy behind that lower layout. So included in the test program were these locations where there was 16-inch by half-inch walls, steel pipe driven. These were driven closed-ended, so they had a boot plate, slightly oversized boot plate on them. That second reaction system consisted of 2 H-pile sections, 2 HP 12 by 53s, and 2 HP 14 by 89s. There were also 2 monotube piles included in the program, 16-inch upper sections with a J33 taper. These walls were 0.2391 inches. And for those of you unfamiliar with monotube, they look like this. They're no longer manufactured, but there are other tapered piles on the market, and we'll see how these perform in the deposits at this site. And the tapered piles, whether these monotubes or the ones currently available, consists of a straight section that gets attached to and driven above a tapered section. For our particular case history, this lower tapered section was 8 inches at the toe, 16 inches at the head of the tapered section, and it was 33 feet long, 32.5 with a taper, and a 6-inch toe at the bottom. So that was what was used in the test program. There were also 2 pre-stressed concrete piles driven, 12 inches square. These were included in the test program as a demonstration project, if you will. a vendor wanted to demonstrate both concrete piles in these Midwestern soils and also his driving equipment. So on his way to deliver some driving equipment in Canada, swung by the project site and drove these two piles for us. They were restruck with other equipment, but they were initially driven with the vendor's equipment, again, as a demonstration project to be included with these other pile types. So here's a picture of the static load test, the two static load test piles to be tested are here in the middle. This is the pipe, this is the monotube. To the left, we have the 4 H pile reaction piles. To the right, we have the 4 pipe pile reaction piles. The two test piles potential test piles not driven are selected for, not selected for static load testing are off here to the right. And the concrete piles are off screen. They're not visible in this photo. Again, very proximate boring location. Here's the conditions at the site. You can see that it's all fine grained granular alluvial deposits right next to the Mississippi River. And the densities really increase here about elevation 660 or so. And then there's a lot of scatter from there down. There's a couple things to note here. Number one, that there are no cohesive deposits in this profile. So as we get to the setup evaluation, keep in mind that generally these fine grained granular or non-cohesive deposits aren't given a lot of credit for setup. So we'll see how that plays out in the results. And note too that tapered piles generally make their capacity best when the top of the taper is wedged into zones in granular soils of reasonable density. So that the tapered monotubes were stopped with their tapers here where that density increased. So to summarize the program, and we'll see why some of these things were done a little later as we go on, 1 pipe pile and 2 H piles were driven to rock. 5 pipe piles, 2 H piles were terminated in overburden. All the monotube and concrete piles were terminated in overburden. And for the piles that terminated in the overburden, multiple restrikes at multiple times, in other words, were performed. The dynamic monitoring was performed on all initial drives and restrikes, with signal matching analyses performed on all initial drives and restrikes. And then, as we noted in that plan view of the test layout, an axial compression static load test was performed on both one of the 12 3/4 inch pipes and on a monotube pile. So we were driving multiple pile types and sections at multiple depths and therefore driving resistances, and at multiple times for the restrikes. And so we had multiple hammers available to us on the project site. The 3 diesel hammers were used for initial drive of the pipe and the monotube and the H piles. The Yuntan hydraulic was used on initial drive of the concrete piles, and the diesels were used on restrikes for all the piles. Now, one key thing that we have to keep in mind when we're trying to characterize setup or any type of capacity characterization is that the blow counts have to be within a reasonable range. That range is generally, and these are generalizations, but that range is generally thought to be between 30 and 120 blows per foot. At blow counts less than 30, the pile is moving so fast, it has such a large set, that signal matching analyses may have a hard time differentiating geotechnical resistance from inertial resistance. And so the capacity might be over-predicted. At blow counts greater than approximately 120 blows per foot, the pile's not moving, the soil isn't failing, and so the geotechnical resistance may be under-predicted. And so as we go forward in looking at these multiple restrikes at multiple times, at multiple depths, on multiple pile types and lengths and sections, we have to keep in mind whether our initial drive blow count is less than 30, between 30 and 120, where it's reasonably estimated, or greater than 120. And same thing for the long-term restrikes. We have to try to choose a hammer and fuel setting on that hammer. If it's a diesel or a hydraulic, either one, they're both variable energy type hammers. We have to choose the hammer type and fuel setting such that we get a restrike within a reasonable blow count. Otherwise, given these 9 potential scenarios of blow counts less than within that range or greater than that range, you can see that of these 9 potential combinations of blow counts at initial drive and restrike, there's only one combination where the setup is reasonably estimated. So this can become an art in the field to try to determine which hammer, which fuel setting to use for an initial drive or a restrike so that you reasonably estimate the setup. So given that background, let's look at how the long-term allowable load profiles are determined. So here's some typical results. This is for one of the 16-inch closed-end pipe piles. Vertical axis is elevation. Horizontal axis is unit shaft resistance pounds per square foot. So the pile toe is down here. This is on a end of initial drive blow data from dynamic monitoring on which signal matching analysis has been performed. And this is the shaft resistance distribution then along the length of that particular 16-inch pile at end of drive. Upon restrike, this is that 16-inch pile's unit shaft resistance. Again, pile toe at the bottom and signal matching analyses performed on dynamic monitoring results. Well, we're not interested necessarily in the long-term capacity resistance distribution. We're interested in the setup or the change from initial to redrive. So what we do is we take the redrive unit shaft resistance distribution and subtract from it the initial drive unit shaft resistance distribution. And what that yields is a unit shaft setup distribution. So as the horizontal axis is labeled, this is the profile of the unit shaft setup in pounds per square foot. And you'll notice that even though these are fine-grained granular deposits, this is a full displacement 16-inch pile, and so we're getting some unit shaft setup. This isn't necessarily as advantageous for design as it might be, but converted to a shaft setup profile, it is. So if we take these unit shaft resistances and apply them to the surface area of a 16-inch pipe and sum them from the surface down, we get a cumulative shaft setup distribution. So this predicts how much shaft setup one would have seen on that pile had they stopped it at any toe elevation above the final toe elevation and restruck it. So again, a quick review here. There's about 170 tons of setup on the 16-inch pile in about 140 feet. So a little more than a ton a foot of setup in these fine-grained cohesive or non-cohesive soils. So this is how the cumulative shaft setup distribution was determined for each pile. Now, dynamic monitoring also yields this red line, again, elevation on the horizontal or on the vertical axis, capacity on the horizontal axis. So this is during driving now. The red is the initial capacity determined from dynamic monitoring as that test pile is driven. And you can see that it goes through some layers, it increases, it decreases as it punches through layers and gets down, and this pile was terminated above bedrock. So then we take its initial capacity profile from dynamic monitoring and add to it the cumulative setup profile from dynamic monitoring. And this gives us a prediction of long-term ultimate capacity versus elevation, or for the full depth driving of the pile. Even though we stopped it at full depth and tested it at full depth on restrike, we can estimate what its long-term capacity would have been at any elevation or depth above that terminal driving. So that's how the long-term capacity profiles were determined, by adding initial plus setup. We wanted to characterize, if you recall, some piles were driven to rock, and we wanted to characterize the toe contribution, toe resistance contribution from the rock. And so to do that, you really need 2 test piles at any given location. And this is how that's done. You can drive the first pile to bedrock and you drive it hard. And with dynamic monitoring, you can estimate a toe resistance, and it will be high. That's represented by the large arrow here in the bedrock. But then if you're going to characterize shaft resistance to add to that, you have to terminate a second test pile short of the bedrock, terminated in overburden, so that you can move it, that is, mobilize it, on restrike. So when you stop this second test pile short it has initially a fairly small shaft resistance, and then upon restrike, that shaft resistance has increased. And so through what is sometimes termed superposition, you add that long-term shaft resistance determined from the second pile and the large toe resistance determined from the first pile to get a combined long-term capacity. And that's what then you can use for design. But again, with a very hard end bearing where you can't mobilize this first pile on restrike, it takes 2 test piles at each location to determine this. So if we look at now, we switched from capacity to allowable load. And so we have, what we've done is taken our long-term capacity from a couple of slides ago and multiplied it times a resistance factor of 0.8. And the previous presentation mentioned the benefit of testing in terms of giving you increased resistance factors. And the MnDOT structural engineering group decided to apply a resistance factor of 0.8 due to the testing done on this project. But here we see then the long-term capacity profile multiplied times 0.8 gives us this green line, but then we add the base resistance or the toe resistance from terminating on the rock, and it jumps us way out to here for a long-term geotechnical resistance. And you can see that it's just short of the structural allowable load determined by the structures group. So that's how the allowable load versus elevation profiles were determined. So we've done that for all of the test piles, all the different types, sizes. So now how do we compare? Which is the best to use? What's the decision tool for us? Well, let's talk about what support cost is and how that can be used. Support cost is simply defined as the cost of an installed or constructed foundation divided by its allowable load. So it has units of dollars per allowable ton or dollars per allowable kip. All it is a unit cost for structure support that the ultimate client is paying for. In other words, how much does it cost to put 1 kip or 1 ton of support for a structure and use it in the ground? It's literally a support unit cost. So we're all very familiar with math, and no, I don't think that that's a support cost is a confusing concept. But let's just go through an example here to illustrate a couple things. So recall support cost is the pile cost divided by its allowable load. So in this first example, let's take a medium section pile and drive it to a medium depth. And let's say that it returns a medium allowable load, 50 tons, and it costs $1,500 to install. So that math works out to an installed pile support cost of $30 per ton. Conversely, if you also consider as a viable foundation option a slightly larger section, perhaps, driven deeper, driven harder, it might return a 150-ton allowable load. And because it's a bigger section and going deeper, it's going to cost more, $3,000 per pile. But it returns a smaller support cost. This is a more economical installation in terms of available allowable load. This looks really, this is very apparent to us all because we all work with math, but this is counterintuitive in a number of ways to a lot of people whom you might want to present this concept to. You'll hear the argument that, well, we're driving in this first case history, the first presentation here, we're driving a pile that costs less per foot, and we're driving it shorter. Therefore, it's got to be more cost effective, right? I mean, that just kind of makes intuitive sense until you think about it or look at it like this. The other pushback we get is from the field crews. And they will say, when we had this design on the books, we were getting 10 or 12 sticks in the ground a day. And then you change the design to this, and now we're only getting 6 or 8 sticks in the day. Well, when you look at productivity, the parameter shouldn't be how many piles are in the ground or even how much footage goes in the ground. The deciding parameter in terms of productivity should be how many tons of support get installed. And more often than not, you'll see that these installations, even though fewer piles go in the ground per day, install more allowable loads of support. So that's support cost. Let's compare now among the pile types for this case history. We polled some contractors about average unit prices for the various sections used in the test program. And we got 2 contractors to respond for what I'll refer to as the conventional sections, the H piles, the pipe, and the monotube. And the vendor themselves were the only respondent to the cost for the concrete piles. So these are the unit costs that we used in the support cost comparison for the various pile types. Again, polling 2 contractors for the conventional sections and receiving costs for the concrete only from that specialized vendor. So if you recall, the definition of support cost is cost divided by allowable load. And for simplification, we won't include splices or stop time for splices or anything, and assume that the cost of an installed pile is linear with depth. So here we have pile toe elevation versus installed pile cost. And that's the way a lot of jobs are bid. You know, cost per foot, and the contractor takes splices and downtime for pick and move and things like that into account. So this isn't a bad model. Linearly with depth, it does the cost increase. And we saw earlier how we determine our allowable load profile. And so we're going to divide the cost profile by the allowable load profile to get a support cost profile. So here is pile support cost versus elevation. And this is kind of interesting in that, you know, up high, when you hit some hard layers, you have very low support costs. And then without subsequent hard layers, the cost, and this would be a soft layer where the capacity decreases as you drive through this layer, but your cost is continuing to increase with increasing embedded length. And so your support cost goes up. Then you hit another layer, hard layer, and your support cost goes down. But you've invested enough length between here and haven't gained enough capacity that this higher terminal elevation remains the lower support cost. So this gives you a sense of how the layering affects the cost effectiveness of your driven pile installations. And then we can see that when you add in the toe resistance, the support cost jumps way down, and that the most cost effective capacity, if you will, or termination depth in terms of cost only, is to terminate on the rock. And this is again for one of the 16-inch pipe piles. So these support cost versus elevation analyses were done for all of the test piles as well. And we came up with an example like this, or I should say a summary table of results that looks like this. And we looked at 2 things, either the lowest support cost above a determination depth that was greater than 75 tons, or the support cost at termination. And so a quick, there's a lot of information here, and really what we'll focus on are the costs. And you can see that the HP 48 by 89 had the lowest support cost at termination between the 2 HP sections. The pipe had slightly better support costs at termination, that would be on the rock, than the H pile, probably because it had a larger bearing area and so developed more toe resistance on the rock. The monotube outperformed in terms of support cost, outperformed both of those options, both of the other steel options, the H piles and the pipe, although it had lower capacities at termination, because as we said, it stopped shorter with the top of the taper in those upper dense layers, and going deeper, the taper doesn't pick up any significantly more load. These numbers were a result of terminating on the rock. The monotube did not terminate on the rock, but it still had lower support costs if the design wanted to accommodate these lower allowable loads. The interesting thing too is that the concrete beat, in terms of support cost, beat all the other options by significant amounts. And this was what the vendor was hoping to demonstrate. Although, as you can see, again, the allowable loads are quite a bit smaller than the other sections. So it's up to the designer to decide whether or not these smaller allowable loads are appropriate for the project, and the lower support costs would warrant designing to these smaller allowable loads. This is just the support cost of the pile itself is just one component of the overall project cost. You have to think about schedule. If you're driving lower allowable load piles, you're going to drive more of them, and so the schedule will be increased. Your pile cap sizes will be increased, and so your concrete and rebar and excavation costs for the caps will be increased, and things like that. So support cost is not the overall answer, and you just automatically drive your design to it. But it's a decision parameter that can be looked at, that isn't often looked at this way, but it can be factored in. So I think we have time to touch briefly on setup magnitudes and time rates. This doesn't have to do with the economics of the project or the test program, but it's more of intellectual interest since we compared these for these various pile types. And so for the various pile types, we're gonna represent shaft setup versus log of time. And so these are for the pipe piles. And you can see again that we're in fine grained, non-cohesive, granular deposits. And we're seeing setups ranging from 140 to 200 tons at the depths driven. And so that's not an insignificant capacity to ignore. It certainly adds to the economy, the economics to factor in setup. So this is how the 4 pipe piles behaved or responded. The interesting thing here, at least to me, is that this early portion of these may be excess pour water pressure dissipation driven, and then there's some kind of a kick after 10 days that may be something other than pour water pressure related, like a calcareous cementation or arching or something like that. It's interesting that it doesn't follow a perfectly linear trend after that 10 days, but instead kicks upward. If we look at the H piles, again, H piles are a very low displacement pile, not generally given credit for setup in these types of soils. But again, we're seeing 70 tons of setup, fairly linear again, maybe a slight pore pressure dissipation phenomenon, and then that kick after 10 days, which again may be something besides pore pressure. We only had one monotube pile that got restruck successfully, and it also similarly potentially linear with excess pore water pressure dissipation, and then a kick at 10 days, maybe some other phenomenon. So, and then the concrete piles only got 2 restrikes, so it's hard to draw many conclusions in terms of the kick after 10 days, but again, they had reasonable setups as well. So, conclusions. Dynamic testing, that is at end of drive and beginning of restrike, both with signal matching, can be used to characterize an initial capacity profile, and from which we can get a shaft setup profile, from which we can get a long-term capacity profile, from which we can get a long-term allowable load profile, as well as a long-term support cost setup profile, or support cost profile. When driving to rock or other hard material, the first presentation referenced till can be as hard as rock, 2 dynamic test piles are required. One first to the rock to characterize tow resistance, one stopping in the overburden to characterize shaft setup. And hopefully we've demonstrated that shaft resistance occurs in non-cohesive soils for both full displacement, that would be the closed-end pipe, and low displacement, that would be the H piles. We mentioned that there was that kick in the setup after 10 days, probably from some other phenomenon than excess pore water pressure dissipation. This is more of a personal opinion. I think pile support cost is a great tool, apples to apples comparison. Again, only for the economic consideration in design. It's not the end all be all, but it certainly is a good, valuable design or decision parameter. The monotubes, again, tapered piles are designed to develop high capacities at low embedment depths and low support costs in granular materials. And so it's not surprising that they develop relatively low support costs. But the concrete piles evidenced the lowest pile support cost. But this particular size, the 12-inch square, were limited by structural capacity. So one last conclusion. You know that you're performing a static load test in St. Paul, Minnesota in January when icicles form on your instrumentation. So hopefully that leaves you on a high note.
But thank you very much for this presentation. A lot of food for thought. We really need to look at some things in a different way, and I'm looking forward to the Q&A at the end, because what you mentioned, the support cost is something that in your mind should be really considered. The question comes up, how can we convince owners and other project teams to start doing that? But for now, thank you very much, Ven, for once again a very good presentation.